Hello, folks. In this topic, we will see a sampling of a few other big data systems apart from the data flow systems that we saw in the last topic. Here's an outline. We will cover briefly about key value systems, also called NoSQL systems, graph processing systems, and machine learning systems. Notice that none of these three are going to be included in the syllabus for your final exam in this edition of this course. Let's dive into key value systems. The basic idea of key value systems was to have a very simple API for putting and getting records very quickly. Okay, so the basic use case is think of a website like facebook.com or amazon.com or twitter.com, where they have a lot of profile information about users or about products that have updatable entries. Like imagine you're posting a status message or you're updating your information or posting comments to someone. So these sorts of records are going to be inserted and then retrieved based on a key, and the value of the record is a general semi-structured object. Okay, so that these days it's often a JSON object. So these sorts of key value stores can also be called document stores. The basic requirement for some of these websites, like we saw earlier, was availability. You cannot allow facebook.com or amazon.com to freeze when somebody is updating a particular record. And if you have tens of thousands or even millions of concurrent updates to the database based on these update queries that come over the internet, you cannot have the website freeze. Okay, so they wanted really high availability. And they wanted high scalability. Clearly, because of the numbers of concurrent queries, they need to operate on very, very large clusters, tens of thousands, sometimes even hundreds of thousands of machines. And as I mentioned earlier, because of the CAP theorem in distributed systems, this meant that they had to sacrifice on consistency. And one of the monikers that is applied to the way that consistency was approached by key value stores is eventual consistency. And the way I summarize this is it's very crude, but this is the following. Throw out all the lessons from ACID that we learned in database transaction management, 30 years of research and development and industrial usage by companies in banking, retail, telecom, and so on. And instead, they just cooked up a system that can let the data become garbage temporarily, but in the best case, it eventually becomes consistent across all the replicas. Now, there was an acronym that the people in the key value stores, the distributed systems world coined. It's more of a, I don't know, what do you call this, backronym? It's something that they just had as a tongue-in-cheek acronym, BASE. Of course, if you know chemistry, acids versus bases. And so here BASE stands for basically available, soft state, and eventually consistent. So you can see availability is the most important thing that they're emphasizing. And then soft state, they don't care about replicating of the entire database, and eventual consistency. Values of the replicas will eventually converge to a single consistent value. But in between, you can expose inconsistent values of the data to the application and to the users, and sometimes the data might never become consistent. If you noticed in some situations, comments or emails on these websites appearing out of order, part of the reason is the consistency issues that they have for their backend key value stores. Now, because they wanted these for web programmers, so people who are building these websites, these web programmers were happy programming in whatever imperative languages they wanted. They did not like writing SQL queries in between to query an underlying data storage system. So they called it NoSQL, which is sort of an RDBMS hating movement. And of course, if you think about it, based on what we saw in this class, it's a totally nonsensical term because it conflates two different things. What they really cared about was the underlying transactional management guarantees and the API for putting and getting. But SQL is a programming language. You can put SQL on top of a key value store, or you can not use SQL on top of an RDBMS that is ACID compliant. So they are totally orthogonal. Whatever. So that is the movement that is called NoSQL. Technical term for these is key value stores or document stores. One of the things you would notice is that even though key value stores were originally developed in this context of these massively concurrent websites, eventually they found adoption in many other settings where you have documents like JSON documents stored. Ironically, they have evolved to this point today that many of these key value stores actually support SQL. So here's a sampling of some of these key value stores. Amazon's DynamoDB was one of the pioneering ones. Berkeley DB from UC Berkeley, of course, is also another pioneering one. I just saw the news day before yesterday that Berkeley DB has won the ACM Sigma Systems Award, which is like an honor given to influential databases, data systems projects. And there's Redis, Cassandra, HBase, MongoDB, CouchDB, a bunch of others. All of these key value or NoSQL systems are also called transactional NoSQL because they allow read-write access to the data. In contrast, Hadoop and Spark, which are also bundled under the NoSQL umbrella somehow by some people, are set apart. They're called analytical NoSQL, and they only deal with read mostly data. Now, the world has come full circle. Many of these key value stores now support SQL as an API on top. Because at the end of the day, if you want to store data in these systems and you want to be able to query them, apply predicates, apply joins, you need SQL. Just doing puts and gets and then doing everything in application code is not going to cut it. So some of these systems now support SQL or extensions to SQL on top of the data they store. In terms of consistency, I mentioned that eventual consistency can virtually lead to garbage data. People realized that was a huge issue. And so in the last decade or two, people have been studying new consistency models that are in between full ACID and full eventual consistency. Like here's an example of different consistency levels offered by Cosmos DB at Microsoft Azure. So geo-distributed cloud-native RDBMS, and they allow you to do puts and gets too. On the left, you have strong, which is ACID. On the right, you have eventual, which means the data can become garbage. And then in between, you have all these levels, and these levels allow you to sacrifice availability. So you can see as you go from the right to left, availability decreases. However, your latency could also potentially increase. Okay, so, but you get more consistency. These bounded staleness, session consistency, consistent prefix, these are all properties of the way reads and writes happen on the database, exploited in a manner that the system can provide more support than just eventual consistency. We will not get into the details of these. I will just note that this area is a key area of research at the intersection of database systems and distributed systems. People are still cranking out papers at Sigmod and VLDB and NSDI and so on to understand distributed transactions. If you're interested in learning more about distributed transaction management, take the distributed systems course, the network systems course, CSE124 or 223B. Moving on to graph processing systems. Now, graph processing has a workload, has been around for a long time, but it's not something that database systems folks used to care much about. But in the last decade or so, it has become a hotter area of research and development. Specialized graph systems like Neo4j have been around for a long time. But ever since Facebook, LinkedIn, and all these social media companies became a big deal, notice that Twitter is only about a decade old. Facebook is only about a decade and a half old. So they are relatively young compared to the database world, which is half a century old. People now study large-scale graph storage, graph querying, and graph processing systems. The basic difference with relational systems is that the data model here is a set of nodes and a set of multi-edges. You could have heterogeneous types of nodes, heterogeneous types of edges, and the operators and the queries that you want to support over these databases are richer graph-oriented queries like nearest neighbor search. Get me the set of neighbors for a given user, or get me the friends of the user. Shortest path queries, connectivity queries, density of the graphs, cliques, and so on. Here's an illustration of a heterogeneous graph that you might see processed in these sorts of graph processing systems. It's a social media graph. You have people, you have locations, you have restaurants, you have cuisines, and so on, and you have different edge types and node types based on the activities on the social media website. Technically, you can store graphs as relations. Nothing prevents you from storing them as relations. You can store one relation per node type, one relation per edge type. You can have edges as with foreign key relationships to people and node types. And if you want to do reachability and shortest path and all these sorts of queries, there is a way to convert them to SQL. You can use recursive SQL. However, we know that transitive closure and repeated self-joins that are involved in these kinds of queries could become quite inefficient. on a regular general purpose relational DBMS. That's why people set about rebuilding the graph storage and physical layer and the operators, physical operators, tailored towards graph processing. Here's an image that I just took, more recent image for the graph processing systems landscape. There's the graph DBMS on the left. There's multimodal, multi-model, RDF, which is like a property graph, triples for what's called semantic web applications. Then at the bottom, you have general purpose distributed graph computing engines like Spark GraphX, Apache Giraffe. Among the graph DBMSs, Neo4j is the most popular, perhaps. And then you also have commercial ones like Tiger Graph, which is a startup here, actually founded by a UCSD CSE alum. And one of our faculty members, Alan Deutsch, is involved with them as well. And then you have commercial cloud vendors also providing graph processing systems, like Neptune from Amazon is a very industrial strength graph DBMS. And then you have a bunch of others, startups, DBMSs created by web companies like Twitter's FlockDB and so on. Graph processing systems and graph database systems are a hot area of research and development right now in the database and the systems and the algorithms world. How do you tailor the physical layer and the storage of data, of graph data, to make graph queries efficient? That's a hot area of research. To do that, you need to understand the behavior of graph processing algorithms and how to store the graph data and how to process it and return query results. And if you're interested more in understanding graph analytics and graph querying and graph storage, take the CSE104 course that is offered in HDSI. Amarnath Gupta teaches that right now. And there's also a Coursera course from UCSD on graph analytics that you could take. Moving on to machine learning systems. Now, machine learning systems essentially take this notion of data analytics that we saw in SQL. So we have group by and analytics queries in SQL. And then they just, you can view them as more advanced versions of analytic computations. Okay, so mathematically, they might do more sophisticated things like inner products and rule exploration and matrix multiplications and so on. So you can see more advanced statistics, data mining, machine learning, including more recent deep learning computations. The way I look at machine learning systems, you can categorize them in various ways. Two orthogonal dimensions that I use to categorize them. Are they packages of ML algorithms, or are they more general purpose language-based systems where you provide a linear algebra style language? Another orthogonal classification is, are they using an existing data system as a platform underneath, so the physical layer and the storage is just reused, or are they a customized system? Are they built top to bottom from scratch? Let's look at each one of them. The packages of algorithms layered on existing platforms were among the oldest forms of machine learning systems. They've been around for almost 2 decades now. Since the early 2000s, Microsoft, Oracle, they all released these commercial tools integrated with their RDBMS. Okay, so these are called in RDBMS ML systems. They use the RDBMS extensibility mechanisms like user-defined functions, user-defined types, user-defined aggregates to allow you to implement machine learning algorithms like logistic regression with gradient descent, k-means clustering, support vector machines, and so on. And what this means is now your training data for your ML algorithm can sit in the database as a table. And that means it can be very large. It can be hundreds of terabytes even. And these ML algorithms will now scale automatically to disk resident data without the user having to sample them and bring the data into memory to run in-memory toolkits like SAS or R or Python or whatever. Apache MadLib is the most mature open source in RDBMS tool. It was built for PostgreSQL and parallel version of that called Greenplum, and it's available as an Apache project. And I myself, some of my prior research have contributed to Apache MadLib, both for statistical learning and more recently for deep learning. So you can go check that out if you're interested. More recently, once data flow systems started taking off, things like MapReduce Hadoop and Spark were also used for machine learning. Mahout, for example, is a library on MapReduce Hadoop where they've implemented a lot of machine learning algorithms using the map and reduce abstractions in Java. And so now you can run that on a cluster in a scale out fashion. I mentioned earlier about the chat that I had with China Mobile, the head of data analytics at China Mobile. I mentioned that they were paying 20 million per year to Oracle in licenses, and this was 6-7 years ago. What they did was, because of that, they did not want to do in RDBMS ML. They didn't want to run Oracle data mining. Why? Because then their Oracle instances will be used for running training, which could be very long running. It could take overnight, could take a lot of hours. And then that means they'll be blocking their transaction processing. OLTP workloads will get killed. And they didn't want that. And so what they did was they just copied their entire data that they needed for machine learning, exported it and copied it to a Hadoop cluster, and they ran Apache Mahout. This was back in the mid 2010s. Now, probably a lot of companies that were using Mahout might have migrated to this MLlib or machine learning library on the Apache Spark environment, which is very similar to Mahout in the sense you have to re-implement ML algorithms using the RDD API of Spark. And that's what the library has: logistic regression, k-means, bunch of other ML algorithms are available on those systems. So the key challenge here over the last decade and a half, it was a hot R&D topic in both academia and industry in the intersection of databases and machine learning. And the basic goal was to rewrite statistical algorithms, ML algorithms, cast their computations in a manner that can utilize these APIs these systems provide. So for the RDBMS, it would be the extensibility abstraction of the RDBMS, the user-defined aggregates and so on. There we had a research project when I was a grad student, Bismarck, that eventually got contributed to Apache MadLib. That's where how you layer the computations of stochastic gradient descent into these abstractions. That's what we talked about. We also showed that that can work in the MapReduce context. Oracle kind of shipped some of that work from my prior research. Similarly, on the data flow side, you have to cast these computations onto these APIs of these systems so that you can run them on top of these systems without modifying their internal code. These days, it's become less active of an area because a lot of the machine learning world has moved on to deep learning. So that's what we're going to see next. Deep learning computations are a form of machine learning computations where a lot of the processing happens as part of the model rather than on the data. If you've taken a machine learning course, this would be called feature engineering. Deep learning is particularly suitable for unstructured data, like text and images and audio and video and all of that. But a lot of web companies are also using this unstructured data and multimodal data. Because of the rising popularity of deep learning over the last half a decade to a decade, custom systems were built from scratch to support easy specification of deep learning workloads and easy training and execution. TensorFlow is probably the most mature and most widely used. PyTorch from Facebook is also popular, especially among deep learning researchers. And so these two systems have gained massive adoption, and they are still subject to a lot of research and development. Concurrently, there was also a separate system called XGBoost that came out of University of Washington. And this is a tree learning system. So again, if you're taking a machine learning course, decision trees and their kind of derivatives like random forests, gradient boosted trees, these are all a different access pattern, different way of computations over the data compared to, say, deep learning. And so these systems, these XGBoost and similar tree learning systems have a very different stack, very different data layout and memory access behavior and so on. Tree learning methods are particularly popular on structured data. So if you look at the Kaggle.com surveys of data scientists, it will show you that 2/3 of data scientists still work with relational and structured data for their applications, primarily because in enterprises, relational data and structured data are the most business critical form of data. And tree learning methods still remain super popular on structured data. Last, let's talk about increasing trend to do cloud native machine learning systems and what is called automated ML or auto ML. Amazon, Microsoft, all these cloud providers, they have built their own custom implementations of all these ML algorithms on top of their cloud native infrastructure. SageMaker is a mature system. Azure ML is a mature industrial strength library for training algorithms at scale. They also have inference and other machine learning related capabilities. They have UIs and dashboards to specify the computations. So you can rent them on a pay-as-you-go manner. Obviously, you can get EC2 or EBS and then run your own scikit-learn or whatever libraries you want. But if you want to do it in a cloud-native manner with elastic scaling, then you would use these cloud-native ML algorithm packages. AutoML basically refers to the ability to build ML models without having substantial ML expertise. When you're building an ML model, you will have to tune a lot of knobs. You have to select features, you have to tune hyperparameters, you might have to select architectures or algorithms. Some of these commercial tools like DataRobot, H2O, and Salesforce Einstein are automating a lot of those steps by incorporating heuristics and domain-specific intuition that they have into the algorithms. And so now you can just upload your data, tell what the target is, what the inputs are, and it'll figure out how to build a model for you. Of course, under the covers, it might use a lot of resources. So there's still a lot of work going on in this space. Each one of these custom systems, whether it is for deep learning, whether it's for tree learning, whether it is for cloud native execution, or it's for automated ML execution, they have their own sets of challenges and ideas. And so all of this has led to this whole area of machine learning systems emerging as its own research area within computing. In the last couple of years, it has kind of forked off from existing areas of computing, like computer systems, like AI, like databases, the compilers, architecture, and that has now led to a new community called the ML systems community. And this is a hot topic of both research and industrial development at the intersection of machine learning, databases, and systems. My own group's research revolves around a lot of these questions in the data systems for machine learning context. Last, let's also talk about the non-package based stuff, which is like a language-based stuff. Linear algebra systems, in particular R and R-like languages, maybe NumPy and Python, MATLAB, SAS IML. These are very popular among statisticians, people who have a statistical background, econometrics background, business analytics. They write these scripts using matrix operations on primarily structured data. R is not particularly popular for unstructured data. And so industry has taken this up, open source community has taken this up. They have layered R on top of existing platforms. So if you look at the second orthogonal dimension, R on top of RDBMS resident data, Oracle R Enterprise, SAP has the HANA R. Then in the open source world, SystemML, it's an Apache project on Spark. Spark R is also a project in the Spark ecosystem. You can write R-like scripts, linear algebra scripts to manipulate structured data in these settings using these layered platforms. So now your data can sit on HDFS or on the RDBMS, and you can write these scripts that will automatically scale to these data transparently. Last one, customized platforms were also studied in this space. Scalapack is a long-running library project that allows you to use BLAS-like efficient, hardware-efficient linear algebra code in a distributed setting. So it kind of comes up with intelligent ways of tiling data to distribute the computations. Revolution R was a startup that also did something like that commercially, but Microsoft acquired it, and I don't know what happened after that. I think Microsoft just wrote it off. It never was a big commercial success, but that's also another platform. So in this whole R-based systems world, it was a hot area of industrial R&D last decade. There was some academic research. However, it's not that active now. It's no longer that popular. A lot of the action today is in the deep learning world. It's in the tree-based learning world, cloud native, and AutoML that we talked about in the last one. To summarize, this whole space of scalable and efficient systems for doing advanced data analytics using machine learning has become very crucial for unlocking the value of big data. Okay, so you need to analyze data in a more sophisticated manner than what just simple SQL analytics can give you, just descriptive statistics. So you want to be able to do predictive analytics, you want to be able to do kind of more sophisticated learning and training and all of that. And that's one of the values of big data. And so machine learning systems have gained more prominence. If you're interested in learning more about machine learning systems, feel free to go check out my book that came out last year. This is the first book on the area of machine learning systems. It looks at it from a data management database standpoint. So now that you've taken this course, you'll be able to understand a lot of the material in there. However, be one that this book is written with a graduate level audience in mind. So it's mainly meant for students interested in research in this space, for faculty, for PhD students, and maybe advanced master students. But if you're really interested, you can check it out. It should be relatively clear what you need for background, what you need to read. If you haven't taken a machine learning course, then I would recommend taking a course before you go check out this book, just so that you understand what these algorithms are and how they work. One thing to note is that the book hard copy is available for purchase on Morgan Claypool, but thankfully on academic networks, on university networks, the PDF is free. Morgan Claypool has kind of contracts with universities that make their PDF for these books available for free. Right now, since we're in remote setting, you cannot access the UCSD network directly. Use the VPN, the UCSD VPN, to go and click on the PDF link, and it should be available for free. If you have some trouble, just feel free to drop me a note and I can send it over to you. And last but not least, if you're really interested in learning more about the data systems aspects of machine learning workloads, what is data preparation, how do you do scalable and efficient model building and feature engineering, and how do you support different kinds of workloads, whether it is tree learning or deep learning, or just statistical learning, how do you do model deployment and inference at scale. All of these issues I will cover in my CSE291 in fall 2020. So that's this coming fall. It might get listed as 234 number. There's some uncertainty there. The registrar's office got something delayed. So I have taught this as a 291 in the last 3 years. So you can check out the link on my homepage as well. But this edition for the fall will not have a project component. Instead, it'll have quizzes and exams. So it should be amenable to a larger number of master students and also advanced undergraduate students. Okay, so go check out Data Systems for Machine Learning. The course description must have been released by the staff. The prerequisites for this course that I'm going to be teaching are you should have taken a machine learning algorithms class like CSE150 or its equivalent, and you should have taken a systems-oriented class like this 132C, which you've already, of course, taken. If not 132C, even 120 or something equivalent to that, or say DSE 102, Systems for Scalable Analytics, that one should suffice too. Okay, just to reiterate, this whole topic of other big data systems, key value stores, graph, and ML systems is not included for the final exam of this edition of this course. And with that, I will wrap up this topic, and that's a wrap of this class as well. Thank you for taking CSE 132C. And if you haven't filled out your course eval scape, please do so as soon as you can. Thank you.